Python's Global Interpreter Lock, GIL, is crucial in managing access to Python objects, ensuring thread safety. However, it can limit multithreading performance. To overcome this, multiprocessing can be employed, allowing parallel execution across multiple central processing unit cores, enhancing performance for central processing unit-bound tasks. Understanding these concepts is essential for optimizing Python applications. Python concurrency involves executing multiple tasks simultaneously, optimizing central processing unit and input-output resources. It enhances performance by overlapping computation and waiting periods, crucial for responsive applications. Understanding concurrency is essential for leveraging hardware capabilities and ensuring seamless user experiences in modern software development. Concurrency in Python allows multiple tasks to run seemingly simultaneously, optimizing CPU and I/O resources. This enhances performance by overlapping computation and waiting periods, crucial for responsive, high-performance applications. It's fundamental in modern software development, maximizing hardware capabilities and ensuring seamless user experiences. Threads are the smallest execution units within a process, sharing memory space, and are efficient for input/output-bound tasks due to lower overhead. Processes are independent program instances with isolated memory, suitable for central processing unit-intensive tasks despite higher resource demands. Multithreading uses multiple threads in one process, while multiprocessing involves independent concurrent processes. Threads operate within a shared memory model, enabling rapid communication but necessitating precise synchronization to avoid conflicts. In contrast, processes use an isolated memory model, ensuring safety and independence, but introducing communication overhead. Understanding these models is crucial for optimizing performance and resource management in concurrent programming. For input/output bound tasks like network requests, file operations, and database queries, threads are ideal due to their shared memory model. For central processing unit-bound tasks, such as heavy computations and machine learning, processes are preferred to bypass Python's global interpreter lock, enhancing performance by utilizing isolated memory spaces. The Global Interpreter Lock, GIL, is a mutex that allows only one thread to execute Python bytecode at a time, regardless of central processing unit cores. It ensures memory safety by protecting reference counting from race conditions. However, it limits true parallel execution, constraining central processing unit-bound multithreading performance in Python. The Global Interpreter Lock, GIL, is a mutex that allows only one thread to execute Python bytecode at a time, ensuring memory safety by protecting reference counting from race conditions. However, it restricts true parallel execution across multiple central processing unit cores, limiting the performance of central processing unit-bound multithreading in Python. Python's Global Interpreter Lock, GIL, simplifies memory management by using reference counting without complex locks. It prevents race conditions and deadlocks by serializing bytecode execution. Historically, it was a pragmatic choice during Python's early development, prioritizing simplicity and C extension compatibility. This legacy still impacts performance considerations in modern multi-core environments. The Global Interpreter Lock, GIL, limits Python's multithreading for CPU-bound tasks, achieving concurrency but not true parallelism. However, I/O-bound tasks benefit as the Global Interpreter Lock is released during I/O waits. Multiprocessing offers a solution by bypassing the Global Interpreter Lock, allowing genuine parallelism across multiple CPU cores. In a real-world example, a CPU-bound task demonstrates the Global Interpreter Lock's impact on performance. Sequential execution of a task takes a certain time, while multithreading, due to Global Interpreter Lock serialization and context switching, often results in no speed gain or even slower performance. Both threads compete for the same lock, highlighting the Global Interpreter Lock's limitations in CPU-bound scenarios. Python's Global Interpreter Lock, GIL, can hinder multithreading performance in CPU-bound tasks, as seen with our timing example. However, for input-output bound tasks like network requests, the threading module excels. By overlapping wait times, it significantly enhances responsiveness, as demonstrated by fetching content from multiple URLs concurrently, reducing total execution time. Python's threading module enhances efficiency in I/O-bound tasks, such as fetching URLs. By creating threads for each URL, we overlap wait times, improving responsiveness. In our example, threads fetch content from multiple sites, demonstrating how multi-threading can optimize network operations. This approach is crucial for applications requiring concurrent data retrieval. Thread synchronization is crucial to prevent race conditions. Without locks, concurrent threads can lead to inconsistent results, as seen with the counterexample. By using a lock, we ensure thread safety, achieving consistent results. Locks protect shared resources, maintaining data integrity and program correctness, especially in multi-threaded environments. The global interpreter lock restricts true parallelism in Python, limiting CPU-bound tasks. Multi-threading introduces non-deterministic behavior, making debugging complex due to race conditions and timing-dependent bugs. Shared memory in threads poses risks of synchronization issues, deadlocks, and data corruption if not managed properly. Multiprocessing in Python overcomes GIL limitations by creating separate processes, each with its own memory space and interpreter. This allows true parallel execution on multiple CPU cores. By using the multiprocessing module, CPU-bound tasks can achieve significant performance improvements, as each process operates independently, avoiding shared memory risks and debugging complexities associated with multi-threading. The multiprocessing module in Python allows for true parallel execution by creating separate processes, each with its own interpreter and memory space. This enables CPU-bound tasks to run on different cores, bypassing the global interpreter lock. In our example, 4 processes handle a CPU-intensive task, significantly reducing execution time by utilizing multiple cores. Multiprocessing introduces higher memory usage and slower startup due to each process loading a full Python interpreter. Despite this, true parallelism benefits often outweigh these costs. Inter-process communication can be managed using queues, pipes, shared memory, and manager objects, facilitating safe data exchange and shared state management in central processing unit-intensive applications. Multiprocessing excels in CPU-bound tasks, such as mathematical computations, data processing, and machine learning. It bypasses the global interpreter lock bottleneck, offering near-linear scaling with available central processing unit cores. This makes it ideal for compute-intensive applications, outperforming multi-threading in scenarios like image and video processing. Python 3.13 introduces the -x no_GIL flag, allowing Python to run without the global interpreter lock. This enables true parallel multi-threading for central processing unit-bound tasks across multiple cores. However, it's an experimental feature, requiring careful thread safety practices and thorough testing, marking a significant shift in Python's concurrency model while maintaining backward compatibility. Python 3.13 introduces the -x no_GIL flag, enabling execution without the global interpreter lock. This allows true parallel multi-threading for CPU-bound tasks across multiple cores. However, it's experimental and demands careful thread safety practices and thorough testing. This shift in Python's concurrency model opens new possibilities for high-performance multi-threaded applications while maintaining backward compatibility. To run Python 3.13 without the global interpreter lock, use the command python 3.13 xno-gil CPU intensive threading.py. This script benchmarks performance by creating 4 threads executing a CPU-intensive task. It calculates execution time and checks if the global interpreter lock is disabled, showcasing the potential for improved multi-threading performance in compute-heavy applications. Disabling the global interpreter lock in Python 3.13 results in a significant performance boost for CPU-bound multi-threaded programs, achieving around 3.5 times speedup on quad-core systems. This enhancement unlocks Python's true multithreading potential, making it a powerful tool for compute-intensive tasks. Python developers can now write simpler multi-threaded code, achieving real parallelism without multiprocessing. However, this is still experimental, requiring thorough testing and thread safety. This opens new opportunities in scientific computing and data science. The ecosystem will evolve as libraries adapt, offering global interpreter lock-free optimizations and best practices. Multithreading excels in I/O-bound tasks like network requests, file operations, and database queries, enhancing application responsiveness. Multiprocessing is ideal for CPU-bound tasks, such as data processing pipelines and scientific calculations. Python 3.13's no-GIL is suited for advanced multithreading, experimental projects, and CPU-bound threading, offering new avenues for performance research.